Welcome to my channel, Mainframe Concepts, where we talk about mainframe concepts. We're going to look at what's more efficient: perform, call, link, or load. These are ways of executing a specific portion of code that you want to separate from the main code. There are 5 ways of doing this. You can put them in stream. You can execute a perform. That means code is written with the main source code. You can also use a call. That means that code is written separately from the main code, but when it's executing, you are physically including that with the main code. The 4th is to link the code. So that means the code is dynamically loaded into memory when it is needed. Some of the programs can be loaded only once and executed several times depending on how it's defined. Some of them are actually loaded every time that they are linked. And the last one is load. That means at the start of the program, before that code is being executed, you will load that program into memory. And when it's needed to be executed, then you go to that address where the code is stored in memory. And what will we do in this video? We will write a main routine to execute a routine. We'll perform that routine within the program. We will call the routine from the main program. We'll link the routine from the main program, and we will load the routine from the main program. We will execute these routines several times, and all programs will be written in assembler. Listed here are the software that we are going to use: the Linux Mint host, QEMU virtual machine, Big Linux guest, MVS Tk5, MVS assembler, and all other. The first thing that we're going to do is we're going to perform the module. What it means is that the module is part of the code and it is written within the source code. So now here's an example of the program that you perform in stream. You have here at the start, it does all housekeeping routines, get the parameters, and now it's going to call that DECR subroutine that's in stream, and then it goes back and then it decrements the count and then it executes it again. So the routine is part of the program and is in actuality physically part of the program, and we're going to link it with that name, and we will specify the number of times this iterates in the parameter. So you see here it's executing 100 times, and the next set will be 1000 times, and the next set will be 100,000 times. We're going to submit it, and immediately it's finished. And you can see how quickly it's finished. And we will see the results when we look at the output. And if you look at the status return codes, they're all zeros. That means it executed correctly. This is the assembled version, and it's linked. So what we're going to do is we're going to look at all the times that it used up to execute. We will get the CPU time and also the SRB time. So we'll start our spreadsheet, and we will put the information on the spreadsheet. For the next job, we need to assemble the subroutine, and it's called concept R. It's just basically like a EFBR 14. So now that the job is finished, let's look at the results, and you can see that the assemble was successful. The module was created as re-enterable and reusable, and it is saved. Now that we're done, we can continue with our next program where we call the routine. So by calling it, the concept R program or module is linked with the main program. While the source code is separate from the main program, it is physically linked with the program. The effect is that it is executing it within the same chunk of executable. So we finished, we submit the job, and the job is finished. And now we're going to get the information and put them on a spreadsheet. We're going to work on the third program, and what this program does is it links the module, and what link does is it checks if the module is in memory, and if it's not, then it loads the module. And definitely this will require overhead in terms of checking in memory and also loading it physically into memory. We're now going to submit the job, and as you can see, the job has started and it's still running, unlike the other jobs, which almost is instantaneous. So we have cut the video, and now we show the results of the job, and we're going to place these on a spreadsheet. So now we're doing the next job, and this next job is going to load the module, and then it will execute it whenever it's needed. So the difference between the load and the link is that in the load, the program is loaded and stays there in memory. So there's no more need to check. It's similar to a call, except that the module is loaded dynamically. And if we look at the results, it's also almost instantaneous. And we're going to load the data into a spreadsheet. Looking at the results, I still cannot believe the results of the link. So what I did was I changed the program. Instead of linking to the module, I linked to IEFBR14. My thinking is that because IEFBR14 is now loaded into the system memory, the overhead for loading IEFBR14 would be less. So here's the result of the job, and we're going to put this data onto the spreadsheet. And we can see the results that the IEFBR14 executes faster than the one that we created, mainly because IEFBR14 already is loaded in memory. So now let's look at the result. What you can see here is the results for 100, 1000, and 100,000 iterations for all the different ways that we can execute a program. What we see here is the 100 times iteration, and you can see that the link, even at this point, is showing a high usage of CPU and SRB. Now we go to 1000 and it's more evident. And now we go to the 100,000 and you can see that the CPU usage is quite high for both. We can conclude that linking is not the most efficient way of calling a program, and also that load has similar performance to a call. So that's it for our video, and thank you for watching, and please subscribe and like this video. Thank you.